without further introduction, I'll just hand you over to Magyar Bálint.
Thank you very much, and thank you all for joining. So this is Bug Bounty Year 1. This is from 0 to 16K low to CVE. And this is going to be a brief overview of about a year of bug hunting that I started early last year. But before I begin, I will do a really quick survey. How many of you have participated in a bug bounty program before? Disclosure programs count. All right. How many of you want to participate at some point, maybe? All right, there's a couple. I hope this talk will increase the number of those people. So yeah, let's get into it. Real brief intro, forgot to start my timer. My name's Bálint, my pronouns are they, them. I'm a hacker, I make games, I make music, art, all sorts of creative things. I've actually been professionally a designer for over 15 years. I've recently transitioned over into cybersecurity, and now I'm a red team and validation engineer at the same company where I was a designer before. And I've been hunting bugs since early last year. And real quick about the agenda, we're going to look at the year from like a bird's eye view, just to give you an overview. And the main part of this presentation will be a little bug safari on 4 bugs that I bring you: an SSO bypass, a leak of personally identifiable information, an account takeover, and the client-side remote code execution, with some closing notes at the end. And I'm going to try to include some lessons I learned from each of these bugs for context and hopefully for your learning benefit. Many of you might have more expertise in some of the areas that I'm going to touch on here, but they are going to be explained on a low level for the sake of beginners. This video is going on YouTube as well, so probably a lot of people who are just starting off are going to watch this. So hopefully these bugs will give you some context on this journey, and I hope I can highlight the sort of the increase in complexity as I learned throughout the year. But I do want to preface this that I was not completely new to this. I basically, in the general term of the sense, I've been hacking since I was a child. I started off with computers running DOS. Back then you had to do a lot of tinkering, sometimes even just to get the things you want to run. So there's some background there. I have been a hobbyist developer for many years, making personal tools, video games, little stuff. And I have been working with software developers as a designer for more than a decade, so I saw the sausage being made, and I think that's a very important context here. I have completed several app security-related online courses and did a lot of labs. And as you'll see in the timeline in a second, I would say that my bug hunting endeavor is like bordering on obsession. And I just wanted to give you this context. If you're very new at this should not be a benchmark for what you can and will achieve within a year. I would say I spent an unhealthy amount of time and effort on this, but I hope it will still be educational in terms of what I actually found. Right, so let's move on to a little overview. I actually kept the time for all the time I spent hacking throughout these approximately 12 months. Which added up to about 1,200 hours. You can see a summer break and a winter break there, but other than that, I was basically hacking every single day, averaging out to over the 365 days, about 3 to 4 hours a day. But normally I did about 4 or 5 hours on a weekday after work, and then 10 to 12, sometimes 14 hours on weekends. Yeah, so that's what I meant by obsession. So this is not something that I would recommend replicating, just for context on how much time I spent on this. And at the end of the 12 months, I had 4 low bugs, 2 mediums, 1 high severity, and 1 critical severity, which added up to about $16,000 total. All right, so here comes the main bit of the presentation, where I'm going to walk you through those 4 bugs and sort of illustrate what I've learned through them. Bug number 1 is SSO bypass. I'm going to whiz through this because it's pretty basic. We have a pretty normal web app on example.com here. When you load the main application, it loads. That's it. I discovered dev.example.com, which was a pre-production environment, and it turned out to be protected by employee-only single sign-on. So for context for this, I was basically doing manual hacking. I was observing differences between how the two domains react, what kind of headers I get back, etc. Obviously, for a lot of the paths I was trying, I was just getting the Entra ID, Microsoft SSO redirect. But I did notice something interesting on the main app's proxying behavior. So I noticed a difference in response headers between some paths on that application. For example, on the top level directory, stuff I requested from the server was served from server 1 based on some information from the headers. But when you looked at stuff in the static directory, I got different headers. So that suggested that it was coming from a different server. Please come in, plenty of seats. Started a bit early here. All right, so the bypass was very simple. Dev.example.com gave me the Microsoft SSO, but when I went to dev.example.com/static, the actual web application loaded. It gave me a soft 404, but the actual full JavaScript application loaded, and the app was fully functional after that point. So the bug is info disclosure via SSO bypass. It was a low severity bug, and it got me a $200 reward. The lessons learned here were, this was very early on, so this was very, very important to me as a beginner, and I made the beginner's mistake of basically blowing up the impact in my head. This is the end of the world. I can access a pre-production client code, and the target basically went like, meh. So risk, ultimately the risk and the level of threat is determined by the target, and you can't really do much about it, so it's in your interest to understand that ahead of time so you know where to spend your time. Mind the details, compare and contrast. If I had not noticed the subtle differences for what certain paths returned on the main application, I would have not noticed this difference in how it was proxied, and then probably the way the SSO was configured versus how that kind of proxying was configured was what gave rise to this vulnerability. So try to understand the infrastructure based on what you're seeing. Look at everything with a magnifying glass and take plenty of notes. I'm not going to keep repeating this for all the bugs, but it's so important because oftentimes, even for something simple as this, you don't find it very straightforwardly. You find a little bit of information one day and another one a week later, and after a while you are able to connect the dots. So it's really important to keep track of those notes. All right, moving on to this leak of personally identifiable information. As an overview, this was a large target with many client applications. Many of the client applications shared this admin API. And the way I approached this was basically a very wide recon. Source code review, because as it turned out, this customer had plenty of applications, client applications with source map code, which gave me a lot of information. So what I was looking at here specifically was this admin API. It had a bunch of endpoints, but it basically returned a 401 unauthorized when you just try to do a GET request to it. And the API flow for admin users themselves was pretty standard. You submit a username and password, you receive a JSON web token, and then you request the authorized endpoints with that token, and then you get the response from the API. Nothing special. And as I did my recon on this target, and they had a wildcard domain, so they had extreme numbers of subdomains that were in scope. I did a lot of fuzzing with standard word lists that you will find in repositories like payloads, all the things, or sec lists. And through this fuzzing, I found a pre-production client that had source map client code, which gave me a lot of information to work off of to tailor my word lists. So I used the info in that source code to build a domain-specific word list for this target, which actually led me to find some other clients that the standard word list didn't turn up to me. Let's just call one that's important here, this satellite-dev.example.com. So if you look at this pre-production version of the satellite client, Based on the source, I deduced that it was used for some sort of automation. The code was source mapped, lucky for me. And it consumed the same admin API as the users, the admin users on the main application. But the authorization and the authentication differed from those of actual human end users. And it was pretty simple. Instead of logging in with a username and password, this client just sent the request to the API endpoints, but it had these two special HTTP headers, X client and X key, which contained some form of secrets to authenticate, and then they got the response based on that. So like I said, the satellite client source was source mapped, and unfortunately for them, they did something really bad. Don't hear a lot of gasps, so probably not a lot of Node.js devs in the audience, but this is not a great idea. This client basically pulled in the entire process environment variable context onto the client side, which is not good. And it allowed me to see things when I ran this client in the browser, such as the values for those X-line and X-key headers that were required for this admin API call. So I took those values and I sprayed it all over the list of endpoints I had for this API, but unfortunately I got 401s, except for one endpoint which started spewing JSON at me. It went by like really fast. It turned out it was thousands and thousands of user records containing very sensitive private information. All right, so the bug, pretty simple. It's a credential leak, right, of the X client X key values. Sorry. And it's some form of credential sharing between production and pre-production environments. But that was not the bug. The bug was that when you access the endpoints, you got a 401, but when you had anything in these two header values, you got an OK response with all of the data there. So ultimately, it was a PI leak via authorization bypass, over 10,000 user records. This was a critical, and I got a $3,000 reward for it. Lessons here. If you go wide, then use that information to connect the dots. I had a lot of info about what kind of subdomains this customer had, this target had, with all sorts of clients in there with source code. Use that to your advantage to, for example, tailor your word lists that are specific to that target's domain. I think this is very important. And yeah, I'm going to echo something here that many top hackers say, which is recon is for finding things to hack on. It's really satisfying to just throw a word list at a fuzzer and see all the subdomains pop up and the paths and endpoints and whatever. But if you don't actually go look at them, they're not very useful. So go do that. Two tools there that I found really helpful to sift through the noise and find the things that are interesting. And yeah, it's a good idea to keep track of your IPs. In this case, because it was a PII leak, the target really wanted to make sure that nobody else had accessed that list without authorization. So they asked for my IPs so they could make sure. Right, onto this account takeover. This is going to be a bit more complex. So the actual depiction of this target here is going to be a bit contrived. I had to conceal what the actual target was here, and it's sort of unusual, but bear with me, just focus on the functionality of the application. So they had user-editable sort of public pages. You had to know a unique page ID to be able to view these pages, but they were editable if you logged in with that unique page ID itself, a username, and the phone number. I know, weird, just bear with me. So to look at this visually, we had this view-only state where if you had the unique page ID, then you can just visit the URL and get some non-sensitive data back regarding that user. And then if you wanted to log in, again, providing this page ID, a username, and a phone number, once you're logged in, you get this session cookie, as well as the ability to add that session ID to the URL and arrive at the logged in state, which is going to be very important. And here you could see some more information sensitive to the user, and you could edit some of that data as the user. And we're going to focus on that field called private data there. So my approach here was, again, manual hacking and source code review. And basically, what I tried, what I had the idea for is that since the page allows you to get to a logged in state with that session ID in the URL, maybe if I found cross-site scripting on this logged in state, I can take that logged in, that URL that results in logging in the visitor, send it to a victim, and then have that cross-site scripting trigger. So I wanted to use the private data field for that, which was one of the fields that were editable. And I just started basically putting an innocuous HTML tag in there for the underline just to see if HTML injection worked. But it turned out there was a web application firewall somewhere in between that blocked all the useful characters for HTML injection. So I got a 403 forbidden. But I did not stop here. I remember there were techniques for bypassing WAFs. One of those being no WAF please from the wonderful people at AssetNote. It's actually a Burp Suite plugin, but I just used I just went with manual hacking and used the same principles as they did for the plugin. Basically, it works like this. WAFs have limits on how much of a request, a post request body they will check. And there's a threshold for that, which has defaults between, for most WAFs, between 8 to 128 kilobytes. So if you have your malicious payload below this threshold in the post body, then the WAFs will just ignore it. So that was the idea, prevent the request bit garbage somehow that allows my payload to get through and bypass the WAF that way. So it was a question of finding the right kind of garbage, which I love that I can say that in hacking. And oftentimes that is the task in hacking, the right kind of garbage. And I started basically injecting stuff anywhere I could. For example, the value of the new garbage key here as an example. I got a 500 internal server error, which suggested there were checks other than the WAF before that on some form of validity. I tried the key name. That also gave me a 500. I tried putting garbage outside the JSON structure, again 500. And then eventually I got this unique response for the contents of the email field, which gave me a 400 instead of a 500 or a 403, and it gave me a verbose error about the email field value being too long. So I pushed on and I tried putting more stuff into it, and I eventually got to just spaces, here underscores for visibility. And what struck me was that when I included spaces, I got the response from the WAF instead of any sort of 400 or anything, which suggested to me that there was something happening here that I'm not accounting for. So at this point, I had enough information to sort of try to build the logic in my head, figure out what was actually working, happening behind the scenes. So that's what I did. It looked like there was some form of validity check on the JSON syntax itself. Not surprisingly, it seemed there was some sort of validity check on what kind of keys were present or not present. And then there was a check for the actual values of those fields in the form of are they the correct type, are they below a certain length, and then eventually the question got to the WAF, is this okay to go? So I continued pushing on with the email field, and I added 8 kilobytes of spaces with high hopes, but unfortunately I got the 403 response again from the WAF. So that led me to believe there was a step I might be missing in my own model for what's happening. It's valid JSON, it's valid fields. There might be a trimming of white space at some point, after which the length of the email field value in this case is checked, and then it gets to the WAF. So the task was to find white space characters that don't get trimmed, maybe, but they do contribute to the length of the request. And they are also not considered for the length. So I very quickly found, very quickly got to the 0-byte here, Unicode encoded for the valid JSON. And with a short value here, I just got the WAF 403 forbidden, but when I did the 8 kilobytes, it actually did the bypass. All right, so now we can inject HTML into this logged in state for this malicious actor's logged in page. So I needed to find out what sort of XSS could work here. And I did the classic thing, just injected an image, a broken image with the error handler, popped an alert, great. So we have JavaScript executing there, nothing stopping us. So I started thinking about what sort of payload we could put there that could achieve impact. The obvious one would be to just make a GET request with a fetch call to an attacker control server and maybe pass in the cookie for the logged in session in the URL. But if you paid attention, you might notice there is at least one problem with this, but there's another one too. There was a length limit on the actual private data field length, and it was 60 bytes. So that example, particular example, would not have worked. And the other one is, because we have the session ID in the URL, the person who's logged in is us. So the only cookie we could exfiltrate is our own, which is not helpful. So how did I get around this? My idea was to basically first to get over the length, because to get around the limitation with the like the session overriding, I need to put in a much longer payload, but I was limited in length, so I wanted to basically infiltrate the payload somehow. I remember this technique where you basically use the URL fragment or a hash, the part after the hash mark in the URL, to smuggle in the code. And then just use the stored XSS that we have on the page to evaluate the code from the URL, slicing off that hash. And just as a treat, we can also encode it for base 64, which is still under the 60 char limit. So that's what the payload will look like, obviously much longer with the encoded payload there. But the actual exploitation then looked like this. We have the payload in the URL. We have the stored XSS on the page in the form of the image, evaluating the code from the URL. And then the actual payload itself, encoded, is something like this. We find a container on the page. We replace it or inject an iframe that is pointing to the legitimate login screen itself on the target. And we add some CSS to basically blow it up and cover the malicious attacker page with a legitimate login page. And then we have some code in the background that checks for the login page actually being filled, so we can, as soon as we can, exfiltrate the data. So visually, it looks like this. We have our iframe injection with the login there, and then we add some CSS to blow it up and just conceal everything. So the only thing the victim can see is a weird URL, but I think we're pretty used to that in 2025. So yeah, that's phishing using the legitimate login page itself, which I found very amusing. And it was this WAF bypass to stored XSS to DOM XSS, eventually leading to account takeover. The severity was medium, and there was a $500 reward, which was a little disappointing because, yeah, not all programs cap account takeover with XSS at medium. It makes absolute sense in the CVSS world when you evaluate the actual attack. But as a hacker, obviously, I spent a lot of time on this, and $500 didn't really seem measurable. All right, yeah, so some lessons learned. Learn your targets framework. The way I found that XSS was actually by looking through the React code for this, which was source map. React has this attribute called dangerously set inner HTML, which is a dangerous thing to use, and this particular app used it. But if I didn't know the basics of React, I probably wouldn't have even searched for that in the first place. So learn at least the basics of the framework your target's using. Don't let a WAF stop you. There's multiple ways around it. And try to understand backbox logic like I did with the API to update the data there. Basically, a scientific approach of tweaking just one thing and seeing what changes in response is a helpful tool for that. Yeah, and this is something I think beginners make a mistake beginners make a lot, which is just stopping at whatever code execution. In this case, if I had stopped at just alert, I would have probably not even gotten the medium payout because it doesn't demonstrate any sort of impact to the customer that is meaningful to them. So keep pushing. Obviously, if you find a critical, like the PII leak I showed you earlier, you have to report that immediately. But if you can escalate something, then you should try. But read the program scope and what's out of scope and what's not, because you can get in trouble. Yeah, and some programs I learned cap accesses at medium, even if it's full account takeover. That was pretty frustrating, but there you go. If you're lucky, the program actually lists in the policy that they do this. That way you can avoid them and get paid. All right, so the final bug here. We have this client-side remote code execution. This was on an app called Google Web Designer, and I can disclose this because this is published now. You can find it on my blog. I'll post the URL later. And it was specifically on macOS and Linux, but this is a Chromium embedded framework application, which is basically like Electron, if you're familiar with that. It's essentially a browser running natively, and then you run a web app inside of it. This is how Slack works, for example, and a bunch of other apps. And this is what Google Web Designer looks like. I wouldn't fault you if you hadn't heard about this before. This is an app that has been out since 2013, making it probably one of the oldest Google applications that are still being updated. Yeah, it's pretty obscure, but apparently it's in use and apparently they care about it. So I hacked on this. Yeah, and it's basically a visual ad editor for HTML5 based ads. And my approach was mostly manual hacking. I did some source code review. The source was minified, so this is JavaScript running inside that native app shell that is essentially a browser. The source code was minified, but that didn't deter me. It's rough getting through minified code, but if you know where to focus, or if you have access to a debugger, which you would for most web applications, for example, then it's definitely not impossible. And it also makes you learn a bunch of stuff about JavaScript, which is cool. And I also used this tool called strace on Linux to monitor the file operations and process execution, because that's not something the JavaScript can do directly. It's done by the app shell. All right, so this vulnerability has to do with the browser preview function of this application. Basically, as a user, you would edit your ad. You want to see it live in a browser. You click a button. It opens your ad in a browser. That's it. Behind the scenes, what happens is you have this folder with your HTML file. We have a bunch of JavaScript boilerplate, all your images, etc. When you click preview, the app creates a folder under that folder with the name GWD preview and then the name of your ad. And this is the vulnerable operation. And then it copies everything under that in a flat structure. And it then launches a local web server and basically uses that preview directory as the root of that web server to show you your ad. This is required because all of the weird JavaScript stuff that Google is doing with Google Ads that is calling out to other servers. I don't know, you can't just open a local file and show it to you like that. All right, so let's zoom into that vulnerable copy action. Normally, this wouldn't be anything special. You have your friendly ad folder there with an assets folder. And then it has an HTML file, and under the assets, there's an image. And when you click preview, that preview directory, oh no, my laser pointer doesn't work. Ooh, almost. Anyway, so there's that directory create there for the GWD preview friendly ad, and then the structure gets flattened into just a list of files based on the parent directory's contents. A little aside on symbolic links. I'm assuming most of you know this, but just a brief explanation here. Basically, on many operating systems, you can create these virtual files that point at other files. In this example, my cool link file, when read by an application that follows symbolic links, would lead to the contents of test.txt instead. And abusing that in combination with this copy mechanic, what an attacker could do is include that preview directory already as part of the malicious package, and then in that directory have a symbolic link that points to somewhere nasty, and then have an asset with the same name as the symbolic link, which will then get overwritten following the symbolic link to that nasty place. So in this case, because the preview directory already exists, when you click preview, it doesn't get created, it doesn't get deleted or anything. Your add HTML file gets copied in there, and then your assets get copied in there. And in this case, the asset has the same name as a symbolic link in the preview directory, which gets followed to place a nasty file. So that's arbitrary file writes. We can create or overwrite files in this manner. It can only write into existing directories, though. So those were the constraints I had to work with to find a way to escalate this. I could have stopped at arbitrary file write, but I had learned that it often leads to RCE, so I was really interested in finding how that was possible here. All right. So I found some naive techniques as a beginner. I'm sure there's plenty more where this came from that are much more efficient and elegant. But what I found was on macOS, you can basically plant a launchd agent, which is a descriptor XML that tells the operating system what to run, and it allows you to run arbitrary scripts. And on Linux, I decided to go with this overriding of the HTTP and HTTPS URL handlers so that when the user clicked on a link anywhere outside of a browser, essentially, whether it's an email or even inside the web designer application itself, it would launch the malicious handler instead of the browser. So on macOS, I had to plant one file, which is this XML file in this plist format, and it just runs a script that pops up a dialog with some user information in it, as an example. And then on Linux, we actually need two files. One is the desktop entry that defines what to run, and again, it's a dialog that pops up some user info and system info, and then another file that actually defines the handler for HTTP and HTTPS with a reference to this desktop file. And then what we need to do is we need the right symbolic links in the preview directory so that these files, these payloads, end up in the right locations to cause some havoc. The problem was all these files needed to go under the home directory of the user, for which the attacker would have had to know the name of the user ahead of time if we were to use an absolute path. Luckily, symbolic links can be created for relative paths. So if we had symlinks in the preview directory, if we pointed two directories up, we would be in the home directory. But I didn't want to stop here because that would mean we have to expect users to put this add in the home directory directly and nowhere else it would work. But luckily, there's brute force. So if you include a multitude of links that point to various locations, it turns out the application doesn't really care. The copy actions just fail silently if there's not an existing directory there to copy into, where that config, for example, .config directory would exist. So I could just include as many of these as I wanted. I included 6 for my POC to get a bigger impact by reducing the sort of requirements, pre-requirements for this to work. So basically, you have all these copies for symbolic links pointing at various depths, and then you need copies of all the payloads with the appropriate names so that the app takes them and overwrites to follow the symbolic links. And then finally, some HTML to have references inside the add HTML file so that these files get copied in the first place. And ultimately, they end up in a zip file. Zip very handily supports preserving symlinks with this -y parameter, so you can pack everything up and get it to your victims. So ultimately, it would look like this. That's pretty small to read, but I'm going to walk through the steps here. Basically, the attacker creates a zip file with the symlinks and everything, and the directory structure required for this. They distribute the zip file. However, these days it would probably be like malvertising for keywords like cool ad template 2025 or something. And then the victims would download and extract that file, open it in Google Web Designer, and use as part of their normal workflow. They would add their ad to their liking and then use the preview function eventually. And that's when our payloads get placed, and then eventually the code will execute based on what I said before. So the bug here, client-side RC with improper Symlink handling, this was interestingly initially rejected by Google because they said it depends on social engineering and they can't do anything about that. And I argued that you can't do anything about the social engineering, but you can reduce the impact when it happens. And they actually eventually accepted it based on that and got a high severity and an $11,000 reward. And this was also my first CVE, so I'm incredibly proud of this. It was a very fun find. All right, lessons learned. This was the big one for me, and I think many beginner bug bounty hunters. Get comfortable with being uncomfortable. If I hadn't been nudged by a friend I made in bug hunting communities, I would have not went for Google, probably. Because who wakes up after a few months of hacking thinking, I can hack Google, I can hack Meta, I can hack Apple. The good news is these companies are ran by humans as well, and sometimes you find gems like this. This app that we're basically in hiding for over a decade with a textbook Symlink following bug like this one. Yeah, don't get scared by minified code. You don't always fight source map code. Most often you probably won't. But you can use stuff like symbol renaming in VS Code and other IDEs where you can just, because the IDE has some sort of logical representation of the code that you're looking at, it doesn't do a find and replace. When you rename a symbol, it actually only renames the relevant symbols. If it's in the local context for whatever function, then just there. So eventually you can, by focusing on the parts of the application that are interesting to you in terms of return on investment, you can start filling in the blanks, renaming stuff, and figuring out how the code works. Yeah, and there's a whole world outside of the web. It would not have occurred to me to try to hack a native app. Obviously, this is a web app running in a native browser, but this happens a lot, and there's plenty of apps that work like this. And I think there's very interesting things happening when those security boundaries are crossed. For like the JavaScript itself can't directly write files, but it interfaces with the app shell somehow, and then app shell interfaces with the operating system, which leads to stuff like this one. Yeah, and dig deep into the scope. Like I said, this app's been out since 2013, probably with this preview function in there, and for 12 years, nobody found it. It's mind-blowing. Yeah, and argue impact, but in order to be able to do that, you have to understand it yourself. So don't just, keep banging the table that your low is actually critical, but if you can explain why it's high impact, then you might get some return for that. All right, some notes to close out. If you work in tech, and I'm assuming most of you here are in some form, or tech adjacent, you have an advantage. If you want to start bug bounty, you have an advantage. You understand what a server is, what a client is. If you have seen an HTTP request, you are way ahead of most beginners. And not necessarily on the nitty-gritty technical level, but just the conceptual understanding of how computers work, how the internet works, how networks work, how stuff like, JavaScript works. That's a huge advantage. I did say that there's a world outside of web, but I would focus on web first. Obviously, most apps out there are with bug bounties are web apps, and that's where most of the learning material is. I think it's a great introduction. I would highly recommend you join bug bounty related communities. There's all sorts of podcasts, YouTube channels, etc. They mostly have their own Discord channels. It's a really powerful way to expose yourself to a lot of creative ideas. And I have found multiple of my bugs because of ideas I got from random conversations. Yeah, and it has been never a better time to learn. There is so much educational material out there, whether you prefer to read or watch a video or listen to a podcast, it's all out there. So I would highly recommend it. And ultimately, I think I've learned that hacking is failing but persisting regardless. And I think it's true for basically anything in life that's worth doing. Many creative processes also. You fail, you hit walls, you learn what went wrong, you tweak your approach, you see what changes, and eventually you find something. Thank you.
Thank you, Bálint. We have some time before Kat Fitzgerald's presentation, so do we have any questions for Bálint?
I'll be around, so you can feel free to approach me. I'm happy to answer any questions.
There's the answer. Okay, we just have a few minutes while Kat sets up, and then we'll move on for the final presentation of the morning session. So if you just bear with us, we'll have the next presentation very shortly. Thank you.